Hey guys, welcome back to my channel again. Myself Nag, and today I'll present you my project, one of my project, LLM CUDA engine stable. So what does it actually run to run a large language model in production? So when you send a prompt to something like ChatGPT, under the hood there's a serving stack doing a lot more than just matrix multiplication. There's a tokenizer, a scheduler, and a memory manager, and a KB cache. A set of highly optimized GPU kernels and API layer that turns your request into tokens and then sends the model's response back to you. So I wanted to understand the full stack from first principles, not just PyTorch, not just calling transformers generate, and not just wrapping an existing runtime. So I wanted to build the inference engine myself. So this is my project, LLM CUDA engine, and Y-style version is this is a version 2 of my project. I did the version 1 of these. From here I did the version 2. As you can see, there are many branches. So this is a stable version. I'm gonna say to you how it works. So let's go to the code. So as you can see here, in include there's one CUDA check, and the HTTP library, which I took it from one of the GitHub repo, as well as the same JSON HPP. And then there's kernels CUH CUDA 1, and there's memory pool, there's model.h, there's paged_kb.h, tensor.h, as well as tokenizer.h, and for the source we have kernels.cu, and we have model.cu, as well as paged_kb.cpp and tokenizer.cpp. Question like this appears, like why is decode so much slower than prefill? Why is the kb cache here? Here is the kb cache. Why is the kb cache management such a big deal? Why do inference engines use page memory? Why does the quantization matter so much for serving? Why are LLM runtimes often memory bandwidth bound instead of compute bound? So these are the system questions, and the best way I can know to really understand them is to build the machine myself. So this was an attempt to reconstruct the modern interface stack from the bottom up. So let me show you the architecture diagrams. As you can see here, this is a proposed architecture which I did. This is a high level system architecture. You can go through it. For now, let's zoom in. As you can see here, it's a host layer CPU, and then it has a config parser, read model, config JSON, and layers, and n heads, and n dimension vocabulary size, as well as token sampler, the temperature top key, and repetition penalty, and then BP tokenizer, vocabulary merge, rules, encode, decode, and there's a execution orchestra. As you can see here, it's the optimization layer, CUDA graphs, speculative decoding, kernel fusion engine, and tensor parallelism multi GPU, NCC sharing, and there's the user interface layer. You can see a CU interface, HTTP AI server, the optional REST endpoints, and then streaming token output token by token callback. You can see here device layer GPU, quantization engine, then CUDA kernel library, attention engine, then GPU manager, KB cache manager. So this is a proposed system architecture complete, and these are the single one complete llama transformer architecture with single forward pass, as well as CUDA kernel hierarchy and dependency, GPU memory layout management, and then inference execution pipeline, prefill versus decode. There's KB cache architecture detail. There's optimization, progression, and benchmarking, flash attention v2 internal in architecture, data flow through single decode step, flash attention version 2 internal architecture, multi GPU tensor parallelism architecture, benchmarking, dashboard architecture. So now let's go to the main program. Now let's remake the engine. So now let's run the server. As you can see here, weights loaded successfully from model mix.bin. There's in GitHub repo, there's an example API usage, and then in PowerShell, you can write it. You can go it here, and then you can see that it fetched this from write a short poem about the moon. And how many, what was the speed? It is 181 point whatever. I don't know, not whatever. 181.204452514648444 token per seconds. So here what happened is, at this point, the HTTP request, first it goes to the tokenizer, and then scheduler, and then CUDA inference, and then token decode, and then it transforms to the JSON response. So let's go back to the repo. So here's overview, motivation, architectures, which I proposed, and there's highlights. What I implemented is custom GPU memory pool allocator, FP16 tensor storage, INT8 per row, quantized MLP weights, FP16 plus INT8, mixed precision decode path, RMSNorm kernel, SWI GLU kernel, rope kernel, as well as embedding lookup kernel, paged KV, cached block storage, batched paged attention score kernel, batched page attention reduction kernel, as well as autoregressive generation loop, OpenAI-compatible HTTP API endpoint, as well as decode path integrated with tokenizer encode decode, TinyLlama custom binary export pipeline. What we demonstrated is stable endpoint, end-to-end text generation, OpenAI-style, that post version 1 chat completions, arbitrary prompt ingestion through tokenizer encode path, GPU backend inference server running locally throughout in the range of 50 to 70 token per second in current stable path, historical benchmark milestones up to 131 token per second in prior phase branches. Here we are getting around more than 100 token per second. As you can see, I have many branches. And then the system architecture is divided into 4 parts. One serving layer responsible for HTTP request passing, JSON serialization, prompt ingestion, generation configuration, user facing response formatting, and there's orchestration layer, tokenizer encode decode, batch formation, sequence lifecycle. You can go through it, as well as memory layer, as well as compute layer, and end-to-end inference flow. A single request follows this path. HTTP server receives JSON request. Here it receives a JSON request, and then prompt text extracted. Tokenizer encodes prompt into token IDs. Tokens are wrapped into batch formats. Decode loop begins. Current token is embedded on GPU. So each transform layer, RMSNorm, QKV projection, row, page KV write. You can see here. And then final RMSNorm plus LM head projection, logits copied or reduced for next token choice, token decoded back into string, response returned through JSON API. You can see here, receive prompt, it returned response. And here's experimental evidence, OpenAI compatible HTTP serving with GPU inference. You can see here, it's loaded successfully, compiled, and they write a short poem about the moon here. And then CUDA graph decode execution, we did CUDA graphs. You can see here, program started, allocating 2 GB memory pool, all those. The capital of France is Paris, birthplace of French Revolution, the birthplace of French Revolution, which led to downfall of King Louis and establishment of Republic in Versailles. And then this benchmark demonstrates stable CUDA graph compilation, successful decode replay, as well as integrated TinyLlama INT8 inference. And then there's flash attention and pre-filled decode behavior. You can see here pre-fill versus decode benchmark, we got 6 prompt tokens. Then pre-fill time was 0.081 second, 74.35 token per second, and then generate tokens was 50, and decode speed was 75.14 token per second. And these are the benchmark snapshots. You can see the benchmarks here. Phase 1 benchmarks, transpose, as well as GEM, tensor core, WMA benchmark, and then safe tensors. And there's a end-to-end rest inference. This is the repository structure, and this is the design components, the GPU memory pool. The engine avoids repeated CUDA malloc, CUDA free during inference by using a simple bump allocator. 2 pools are typically used: model pool for long-lived allocations like weights and KV block pools, scratch pool for request activation logics and temporary activation buffers, as well as tensor representation, paged KV cache, attention implementation, rope, RMSNorm and residual fusion, INT8 mixed precision feed forward, tokenizer, HTTP API server, model export pipeline. Then there's build instruction, as I said you, then run it. And then it's example API usage, which I showed you just right now here. And then you can use the curl. And these are the supported current capabilities and not yet fully generalized. A little bit has been done, CUDA graphs as well as top K sampling, and then beam search has not been done that much yet. Then multi-GPU tensor parallelism is left because for making this I need a system with 2 NVIDIA GPUs, but mine one is now RTX 4060 laptop GPU. So this is the performance notes, 38 tokens to 70 tokens depending on prompt, batch size, and then server path here. Historical prior batches demonstrated 84 tokens with CUDA graphs plus INT8, 131 with page attention continuous batching. These numbers are sensitive to GPU model, Windows and versus Linux driver overhead, batch size, prompt length, current decode kernel path, as well as legit copy sampling strategy. So the research relevance, you can see here, I can go through it. Lessons learned. During export or runtime mismatches are catastrophic. If Python exports FP16 but the C++ loader exports INT8, output becomes pure garbage, even though the code runs. And there's example output. There's behavior, future work, short term, medium term, long term. And this is acknowledgements. So that's the project. From scratch, CUDA LLM inference engine in C++ with custom transformer kernels, paged KV cache, INT8 mixed precision, tokenizer encode and decode, and OpenAI-Style HTTP server on top. This was one of the most educational system projects I have done because it forced me to understand the exact boundary between model architecture and infrastructure engineering. If you ever wanted to know what sits underneath a modern LLM API, this is basically the path. If you want, I can also make follow-up videos on page attention in detail, why decode is memory bound, how quantized GMV works, or how to benchmark this system properly. Thanks for watching. If you find this interesting, feel free to like, subscribe, and check out the repository below.